Welcome to video 2, the second video covering chapter 1. We're going to pick right up where we left off. We're going to talk about sources of data. Data for statistical analysis comes from many different sources. Generally speaking, you can either use existing data or you can generate your own data. Ways of generating your own data are to run a controlled experiment or perhaps to issue a survey and collect survey data. Oftentimes, however, we will use data that already exists that comes from, for example, internal company records. For example, Human Resources Department collect a lot of data on employees, their training and education, their salaries, etc. Data for an analysis may also come from business database services such as Dow Jones. Data may come from government agencies. The government collects a lot of data for policy purposes to track different policies. For example, the U.S. Department of Labor collects data and calculates things like the unemployment rate and the employment rate. There are industry associations that typically collect their own data. There are special interest organizations, and of course, with the internet, there's just a plethora of data. There are just literally terabytes of data that are out there waiting to be analyzed. You should always be cognizant of the quality of the data that you're using, and it can be quite a task to take data from different sources and match it up so that you have an internally consistent data set. Even if you're looking at different government agencies, the reason the government agencies are collecting data may not be the same reasons that you would like to use the data for. And so getting the data to sort of talk to each other and to make sense within one single coherent data set can be quite a difficult task and a challenge. So data sources in general, as I said, can either come from existing sources or statistical studies, which can be experimental in nature. So in an experimental study, the variable of interest is identified first. Then one or more variables are identified and controlled so that data can be obtained and how they influence the variable of interest. This is more common in natural sciences. For example, we may wish to study the impact that a fatty diet, for example, has on the probability of coming down with cancer. It may be impractical to do a study using human beings because we can't collect all of the variables or control completely the environment that human beings live in. So we may choose to use mice for the experiment instead. And by looking at mice, we can control all of the different things that might influence their probability of coming down with cancer and vary only one carefully controlled variable at a time. That is the amount of fat in their diet. Then we can look at differences in cancer incidence between mice who are fed a fatty diet and those that are fed a leaner diet. The statistical techniques that are used in experimental studies are quite straightforward compared to the type of statistical techniques that are often needed if we collect our data from an observational study. In economics and business, however, often we will be forced to use observational data. So observational or non-experimental studies, there is no attempt, or usually there's just no ability to control for the influence of other variables that might impact the main variable that we're interested in. Again, going back to our example of using human being or human data and looking at the incidence of cancer, we would have to collect data not only on the amount of fat accurately that people have in their diet, but we would have to control for perhaps the state that they live in, their age, perhaps their occupation could have an impact on their likelihood of cancer. Anything that could influence the likelihood of contracting cancer, including previous diseases that people have had, would have to be carefully controlled for in an analysis that would look for the influence of a fatty diet on cancer rates. So these types of studies require much more sophisticated statistical techniques and are typically much more complicated. Unfortunately, in business and in economics, though, we typically can't run controlled experiments, so we are forced to use a lot of observational data. In economics, you typically think of economics as being divided into microeconomics and macroeconomics, for example. But there's a third area of economics which is equally important in both micro and macro, and that is econometrics. Econometrics is really a group of statistical techniques that are specialized towards analyzing observational or non-experimental data. So good techniques are out there, but they tend to be quite advanced compared to the types of techniques that are appropriate for experimentally generated data. Descriptive statistics. I want you to understand right from the beginning of this class the difference between descriptive statistics and statistical inference. Most of the data that you see in a newspaper, for example, or in the media are examples of descriptive statistics. The average of this or the median of that. Most of the statistical information is quite simple and easy to understand. Such summaries of data, which can be tabular, or you can often find nice graphs in newspapers or in magazines. Sometimes the descriptive statistic may be boiled down to a single number, like a median or a mode or a mean. These are referred to as descriptive statistics. The first module in this course really covers descriptive statistics and teaches you the types of techniques that are appropriate for categorical data versus quantitative data. We're going to look at tabular summaries of data, or tabular descriptive statistics, graphical descriptive statistics, things like pie charts and bar charts, and we're going to look at numerical summaries such as the mean or the variance or the standard deviation. Statistical inference is really a step beyond descriptive statistics. This is where we really try to learn from the data. And what I mean by that is that there may be some population out there which is the set of all of the elements that are of interest in a particular study. As an example, just to sort of solidify the discussion here, suppose that we're interested in knowing the average income in the U.S. Economy, looking at U.S. households. There may be a population of 400 million households in the United States. Those 400 million households are going to be denoted by a capital N. So N is the size of the population that we're interested in. Now, if we want to study an entire population, we can do a census of that population. And in fact, the U.S. Census Bureau does a census of the U.S. population every 10 years. It's quite expensive. It's a lot of hard work, and it takes a lot to crunch through that data and release it to the public. So to get more timely data in between the decennial censuses, the Census Department often runs samples of the population. So rather than collecting data on all, say, 400 million households, they may go out and collect a random sample of 500,000 households instead of 400 million. That's called a sample. Then they will take that sample and calculate statistics from the sample in order to learn about the population. That is statistical inference. So statistical inference is the process of using data obtained from a sample to make estimates and test hypotheses about the characteristics of a population. In this course, we're always going to denote the size of the sample as opposed to capital N for the population. The size of the sample will be denoted with a lowercase n. It should be clear that the size of the sample will always be less than the size of the population. Here's a schematic of statistical inference. First, there's a population that we're interested in. Going back to our Walmart example, we might be interested in knowing department sales or average department sales for across all departments and across all Walmart stores in the United States, nationwide. So what we have in our sample is a sample of just 45 stores. That's it. There are more than 45 stores nationwide. There are probably more than 45 Walmart stores just in the state of Pennsylvania where I live. However, if these 45 stores are picked in a way such that they're representative of the distribution of stores geographically across the country, then we can use that as a random sample, and we can take an average of all of the weekly sales across all of the departments and across all of those dates as an estimate of what the true population value of weekly sales is equal to. When I did that, for the data set, I got a value of $15,981. So that is my sample estimate of what the weekly sales value is for all departments across all stores in Walmart nationwide. Statistical inference. Statistical inference is really more challenging. I think it's more fun, and it's more sophisticated than doing the types of descriptive statistics that we're going to do as we round out Module 1 in the next 2 chapters. However, don't underestimate the importance of doing really good descriptive statistics. Building tables, calculating averages, comparing means and medians, plotting your data carefully. That is the way that we identify problems in the data set, and we identify outliers, and it's an important part of doing any good statistical project or data analytics project correctly. In closing, I'll just give you one example from my own personal experience. I was working on a forecasting model for a real estate company that develops commercial real estate in Seattle. I had data for property values all across the Seattle area, and they were trying to identify properties that would be most profitable to develop commercially. In looking at my data, I found one property that had a very, very large value associated with it. Many standard deviations, 15 standard deviations beyond the mean. It was influencing the results of my model. So I would never have discovered that outlier if I had not done my descriptive statistics carefully. Now there's one of two possibilities. Either that observation was a true outlier, or perhaps the variable was miscoded and somebody typed in the wrong value. That's possible. In fact, it happens quite often. Upon further investigation, I found out that that property belonged to one Mr. Bill Gates. I deleted that observation from the final analysis, and it improved the fit of my model.